Hello, this is Math 2270 coming to you from the College of DuPage for summer of 2020, and this is the conclusion of the lecture called Introductory. We define the interval of definition, but this really is the interval of validity. We've talked about that before. It must contain the initial condition, and it must be the domain of the solution. The graph of a solution phi of a ODE is called a solution curve. There may be a difference between the graph of the function phi and the graph of the solution because they might not have the same domain. So the interval of validity becomes a consideration. Also, we can have solutions that are implicitly defined. Here we have g of xy is equal to 0. That could be a solution if at least one function phi, where phi is equal to y, satisfies the relation as well as the differential equation on I. We've seen examples of this as well previously. We have family of solutions when we have a bunch of constants. We can have, when we have one constant, we can have a one-parameter family of solutions. When we have many constants, we can have an n-parameter family of solutions. If we nail it down where we have enough conditions to talk about a solution of a differential equation free of arbitrary parameters, is called a particular solution. Sometimes a differential equation possesses a solution or multiple solutions that are not member of the family of solutions of the equation. That is, solutions that cannot be obtained by specializing any of the parameters in the family of solutions. Such extra solutions are called singular solutions, or I call them loss solutions. We've seen a bunch of these before. Here is another example. We will also talk about systems of differential equations. Here you see dx dt is equal to f of t, x and y. This means that x and y are both functions of t, and dy dt is equal to g of t, x and y, and certainly we could have a much larger system of equations here. A solution of such a system is a pair of differential equations, so you solve for x and you solve for y, defined on a common interval I that satisfy each equation, so both these equations have to be satisfied. Later in this course we will address these. Some remarks: unless it's easy or important or you're instructed to do so, there's usually no need to try to solve an implicit differential equation explicitly in terms of x. I will usually ask you to. A differential equation does not necessarily have to have a solution. It might not be apparent whether a first-order differential equation written in differential form, m dx plus n dy, is linear or nonlinear, because there's nothing in this form to tell us which symbol denotes the dependent variable. We will have problems that will bring up this issue later. And if every solution of the ODE can be obtained from a choice of values of these parameters, then we say that is the general solution. So we have general solutions, we have family of solutions, and we have singular solutions that are now part of our vocabulary. One of the fundamental problems we're going to solve is solving an initial value problem. So in general it will look like this. These are your initial conditions, and there's the differential equation. Together they are called an IVP. So a first-order differential equation is going to look like this. We're seeking something that has a given slope but goes through a specific point, x0, y0. A second-order differential equation also will look like this. We specify not only that it goes through a specific point, but that its slope is a given value. Two fundamental questions arise in considering an initial value problem. Does a solution exist, and is it unique? So the existence question can be parsed the following way. Does a differential equation possess solutions? Do any of these solutions pass through the point x0, y0? And when can we be certain there's precisely one solution curve passing through the point? Both of these questions have examples wherein the answer is no. Hence it's an interesting mathematical problem. Which has a solution with Picard's theorem. This is Emile Picard, shown here. He has two big theorems that are called Picard's theorem. This is one of them. It is not Jean-Félix Picard, who has a crater named after him. He lived prior to Emil Picard, and so they only give craters on the moon one name, and so this guy doesn't have his crater, and is certainly not Jean-Luc Picard, the Star Trek character. But here's what the theorem says. Let R be a rectangular region in the xy plane defined this way, and this contains the initial value. If the right-hand side, which is f of xy, and the first partial of f with respect to y are continuous on R, then there does exist some interval, I0, about x0, contained in AB, and a unique function y defined on I that is a solution. I'm not going to ask you to prove this, but I am going to ask you to interpret this in some problems as we go forward. It is worth noting that the conditions in the theorem, Picard's theorem, are sufficient, but not necessary. Also, even if the solutions do not hold, or the if parts of the theorem do not hold, you can find something that has a unique solution. And based on what we've done before, you should be able to guess that this is going to be y equal to 1 is going to be a solution to this. Initial conditions are prescribed at a single point, x0, but we can be interested in differential equations that are subject to conditions specified on its derivatives at 2 different points. These are called boundary value problems, and they are way important, way different than initial value problems, and perhaps an enrichment discussion in this course. I hope so. In closing, now, more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. God bless.